Hello, my name is William McKillop, and I will be telling you about motion of a falling object, which is our second lab. In this lab, we track the motion of a falling object from rest. In this case, we used a golf ball. After capturing the video, I then analyzed it in Tracker to extract all of the motion data we would need for the lab. In the analysis and construction of models, we will be using Newton's second law, with F net representing only gravity for one model and gravity with the drag force in the second model. And I have these equations below. F net equals F gravity for the first model. F net equals F gravity plus F drag for the second model. And obviously M means mass. G is 9.8 meters per second squared. Drag is negative B times V squared. And here's the video of the ball dropping. Play that again. All right. So the information about this, we have the data points when I drop the ball on the left side, and that's represented with the graph next to it. And also on the right side of this whole slide are the specific data points. So for data and measurements, I had the change in y to be negative 1.804 meters, the change in time to be 0.6 seconds, the mass of the golf ball to be 4.593 times 10 to the negative 2 kilograms. So my code here and Lab 1 share a lot of similarities, but this time I created two different models. The difference between the two codes are the values that make up F net. The image on the top shows the code that considers gravity, while the code on the bottom also accounts for drag force, which requires implementing the value B. So for the gravity-only model, I coded a model to project how the golf ball would fall in an ideal setting using Newton's second law and the data gathered from Tracker. The model without drag was similar to the real position, with the actual position being slightly shorter than the model projection. After accounting for the turbulent drag, there developed a significant difference between the two projected positions. The position with drag was less than the position with no drag. This is potentially due to the small size of the golf ball, since the area that would be exposed to the drag is less than it had been with another bigger object. So, some potential errors of this experiment. Most of the error found in the actual fall could be attributed to the golf ball being too small of an object, and it was difficult for the camera to capture it. Additionally, the time frame recorded for the fall was relatively short and might have shown the influence of drag had more time passed. Finally, the mass of the golf ball could have furthered the previous issues by causing the wave force to be larger than it would ought to have been. And so what does this mean? With the given time frame and causes of error previously stated, I don't believe that the golf ball experienced terminal velocity, but given a greater span of time and space, it would have inevitably gotten to that point. With the introduction of an initial throw or force, this required time would be shortened by starting the fall at a greater initial speed than rest. So what if initially the golf ball had been thrown down, then the terminal velocity of the object would not change as it was falling. The golf ball that is initially thrown down will reach a constant velocity earlier than when the ball is dropped starting from rest. Both graphs end up flattening out, showing that a constant velocity is eventually reached. Terminal velocity remains the same. And here on the top, I have the graph of the golf ball thrown down at 5 meters per second, and also the golf ball dropped from rest in the second graph. And that's it.